Imagine lifting the ocean like a giant blanket. Beneath the waves, you would uncover mountains, canyons, and an enormous underwater cliff. Over its edge flows the largest waterfall on Earth. It creates no visible cloud of spray, and no tourist can stand beside it. From the surface, the sea looks almost ordinary because this waterfall is completely underwater. It lies in the Denmark Strait, in the North Atlantic between Greenland and Iceland. This remote, freezing region is crossed by water masses with very different temperatures and densities. Hundreds of meters below the surface, the seafloor forms a broad ridge and then drops sharply. Water crosses that hidden edge and continues down into the deep Atlantic. But how can water fall through other water? The answer is not magic. It comes down to temperature, salinity, gravity, and one fundamental physical property, density. Extremely cold water flowing from the Nordic seas is denser. When it meets relatively warmer water, it tends to slide underneath it instead of remaining near the surface. Now add the shape of the seafloor. After crossing the ridge, the cold water begins moving down the slope, accelerating toward a basin thousands of meters deeper. This is not a perfect vertical curtain like Niagara Falls. It is closer to an immense liquid avalanche, continuously moving beneath another layer of ocean water. The total drop is roughly 3.5 kilometers. Angel Falls, the tallest waterfall on land, does not reach 1 kilometer. The comparison completely changes the scale. According to NOAA, more than 3.5 million cubic meters of water move downward every second. That volume is almost impossible for the human mind to picture. Imagine thousands of Olympic swimming pools crossing an invisible edge at the same time. 1 second later, the entire scene repeats. Then it happens again, without stopping. After the descent, the water does not disappear. It keeps traveling south, following the seafloor and joining a deep current along the western edge of the Atlantic. Underwater mountains and rough terrain redirect the flow. Large eddies mix its edges with the surrounding water, gradually changing its speed, temperature, and chemical properties. This passage helps form North Atlantic deep water. The underwater waterfall is not the end of the journey. It is one important stage in a much larger circulation system. That movement connects with the global ocean circulation, often described as a giant conveyor belt. Surface and deep currents link ocean basins separated by thousands of kilometers. This system redistributes heat and carries nutrients and carbon through the ocean. The sea is not a motionless container. It is a slow, complex machine that never truly stops. One waterfall does not control the planet's climate by itself. That would be an exaggeration. But the Denmark Strait overflow is an important part of North Atlantic circulation. If this phenomenon is invisible, how can scientists measure it? Oceanographers use temperature and salinity sensors, current meters, anchored instruments, satellites, and research vessels. A single measurement reveals very little. Years of observations at different depths allow researchers to transform speed, direction, temperature, and salinity into a three-dimensional map. The next time you look at the sea, imagine the moving landscape below, rivers without banks, submerged mountains, and a waterfall 3.5 kilometers high. What hidden place should we explore next?